Okay. Okay, so this is the organization of the class for this semester. So you have my name here, and we have a teaching assistant, Fam, and his email. So he will help you to do exercise during the semester. The material we are supposed to cover this semester is first we are going to talk about a little bit about some general description of what is an algorithms, and then we're going to focus on trying to measure the performance, the running time of algorithms, so that the first two chapters, the introduction and asymptotic notation, are material that describe how we can measure the execution time of algorithms. Then, since the name of the course is data structure and algorithms, so we are going to cover some material related to data structure and trees, which are also a kind of data structure. And then we describe how we can analyze the running time of algorithms. So you will know how we can measure the running time, or how we can measure the performance of algorithm in terms of their running time. And then we cover in chapter 5 and 6 technique to analyze the running time of iterative algorithm and recursive algorithm. Chapter 7 is on graph, and then sorting algorithms. And finally, chapter 9 on searching. And finally, 10 is about different type of algorithms. So greedy, divide and conquer, and dynamic programming. So this is the most substantial part of the lecture, actually, chapter 10. The others are preparation for you to see that. We have a textbook that can be used. So the main textbook is this one, Common and Rivas and Stein, Introduction to Algorithms. Let me see if I can find it. So this is the cover of the textbook. I will post it on Team, and you can download it also from the web. So this is the main textbook that the main reference textbook, because I have my own slides. So all that I cover in the class will be on slide also. So you will have slide prior to the lecture. There is a second book that is that will be used. Is the book from Brassard and Bradley. This book is rather difficult, so but sometime I will use a reference from this book in my lecture. This book also can be downloaded from the web. And I will also post it on Teams so that you don't need to search for the books if you don't want. So these are the two textbooks. I don't think there is anything else that I will be using There are lots of textbook, of course. There is this one here, but I'm not planning to use it at all. Other textbook, and that's it for the course organization of this class. Well, there is one more items that I need to discuss with you about how this course will go, and it is the evaluation. Okay, so how we're going to fulfill the university requirement in terms of evaluation. So the actual description from the university for this course is that we have two exams. One is a midterm exam that worth 30% and a final exam that worth 70%. So we have a little bit freedom this semester to make the final exam on two different exams. So rather than having one final exam at the end of the semester, we have the flexibility to have a two-phase final exam, one during the semester and one in the final. That will worth half of 70% each. So, but this I need to discuss with you whether you want this or not. So I will ask you to think about it, whether you prefer to have one final exam or two, or the final exam divided in two sections. So you can think about it and discuss with each other, discuss with your the person that is responsible for the class, and we can have a small discussion next week about what is the way you prefer. So for me, one way or the other, it's okay. You can have one final exam that worth 70%, or you can have two final exams, each working more than 30% each. Okay, so it is up to you. It's easier, I think, to have two final exams because you have less material to prepare for each of them. So they will cover different topics, each of these final exams, as well as the midterm. So the midterm covers some topic, and then final cover a different set of material. So you never have to prepare for the whole semester for preparing for an exam. You always have to prepare for what we cover since the last exam or since the beginning of the semester. So you can think about this, and we can discuss what it is that you want at the beginning of the next lecture. I don't think I have much to discuss. Usually a lecture is four periods. Start at 8:25. I plan to have at least one period per lecture for exercise. And this period will be conducted by our TA, Fam, that will do exercise with you online for the moment. And we will have 3 lectures of theoretical material, where we'll introduce the subject, and then you will have exercise about the subject. Quite often the exercise will be the last period, not always, but quite often it will be the last period. And I will stay online during the exercise, so if you have questions, you can ask me, or you can ask the TA when you do exercise. Okay, so I don't know if I forgot to mention something about the class organization, or if you have question about how we something that is not clear in your mind about how the class will proceed. Okay, so look like everything is clear. So there are two ways you can communicate with me. Is either you use the chat. You can use your microphone and talk to me, or you can use the chat devices on Team. Okay, so look like we can start. And you can always comment about if I go too fast or too slow. I'm not sure what you have covered before, so that might be a situation where you already know what I'm talking about. And in which case you can let me know that you already saw this in other classes, or you saw this in high school, because we really start from the beginning. And if, on the other hand, I go too fast, I speak too fast, or I cover something too quickly you do not understand, so let me know. I will slow down, or I will repeat what you didn't understand. So let's start with the first slide, first set of slides that you have already on Team, which is some terminology that we will be using the whole semester. So this, what I'm going to talk about is a little bit described in chapter 2 in Brassard textbook. At least I got it from there many years ago, so I don't know if it still looks like this or not. It changed a lot. So this is let me shut off my camera so that you can focus only on slide. So these are general, at least for the few first slide, these are general statement. But after that, what I'm going to talk is how we can measure the running time of algorithms. So today we only talk about how to measure the running time of algorithms, at least what we consider to be the running time of algorithm in this class. So I will define what is an algorithm, what is the input size of algorithms, what is the running time, basic operation, and zero rate, time complexity. So we need to differentiate between problem and problem instance, between algorithm and program. And there are some link here for YouTube video that you can watch in order to have an idea about what is an algorithm. So most people don't really know at the beginning what we mean by algorithms. Certainly my grandmother didn't understand anything about this, so she asked me lots of questions about, well, what is this about, and whether this is something related to cars or this is related to goods. I told her, and how can I make money with this? And you know, when I was a student, so she asked me, why do you study algorithms? She said, I don't know what is algorithms. And for my grandmother, there's only two things in the world. Either it's a car and money, or it is God and religion. So she asked me where it is. I said, it is both. It is religion where we can make money. So, because I cannot tell her more than that about what is algorithm. So, but to you, I'm going to tell you much more. Okay, so algorithm, of course, is theoretical. It's not it is not something that we can touch like a car or money. It is more in the mind of people. But we are going to try to make it concrete by providing description of algorithms in writing. Okay, so even though they are there to be seen, these algorithms, the description of algorithms, actually we only understand an algorithms if we can see in our mind how does it works. Of course, algorithms, they are a description of solution to problems, okay? So for now, maybe you do not know what is a problem, except how you can find money to pay your tuition fee, you know this problem, or how you can find a way to get to the school, you know that problem, how you can find a way to see your friends, etc. You are already familiar with problems. What the kind of problems we're going to talk here are problems that people face in engineering or in mostly in engineering, right? You're already familiar, I guess, with some engineering problems. So when we talk about problem, we talk about engineering problem. Engineering problems that are related to computation, of course. So an algorithm is there to solve a problems, but it's not a human being solving a problem. It is a problem solved by computers. Okay, so when we design algorithms, actually we design solution to problem that can be performed by computers. So that's the general idea of an algorithm. So it is some kind of solution that can be transformed into a program, and then that program can be executed by a computer. Okay, so there are lots of ways to solve problems, but the way we are interested here is those that that can be used by computers. Okay, solution that can be used by computer. So, but algorithms are a little bit. Even though we know this is something that it's a solution for a problem that can be solved by computers, they are a little bit abstract also, in the sense that solutions have to be understood in our head. We really know what is an algorithm for a specific algorithm for solving a specific problem if we can see in our head how it solved the problem. So at the beginning, we will be talking about pseudocode like this one here. So this is an example of an algorithm. So it is an example of algorithms written in words. But eventually, you need to go beyond this writing description and try to figure out in your head how this way, what is the way that this algorithm describes for solving a problem. Okay. So algorithms are going to be given to you in this form here, like that we call pseudocode. It is called pseudocode because it looks like programming code, but it is not detailed as a programming code. We recognize a few things like for loops, okay, if condition, assignment, variable declaration, etc. But we don't specify, for example, that this array is an array of integer or float. We don't specify that this variable is an integer or other types. So there's a lot of things that are omitted in this description that make it unfit for programming. Okay, so when you want to program this thing, you need to add a lot of other information that are needed for the computer to be able to execute, and also for the compiler to be able to transform the code into binary executable code. So this is an algorithm that solves a specific problem. The problem that is solved is that is to find a sequence. So A here is a sequence of array. It's an array of integers, and we want to find a sequence of these integers so that they are not in they are in increasing order. Okay, so we want to solve this array in increasing order. So we want the first element of this array to be the smallest one, and we want to be the last element of this array to be the largest one. And we want to compare each element. We want to have a relation between each adjacent element in the array such that the one on the left is smaller or equal than the one on the right. Okay, so that's what we want to get. That's the problem we try to solve. Okay, and this description here is telling how the computer can solve this problem. So that's why it is called an algorithm. We are trying to make a differentiation between problem and problem instances. At this moment, maybe here this will seem to be a little bit too abstract, or you do not know what I'm talking about. But it is important to distinguish between problem and problem instance, because the description of algorithms is to solve a problem, not a problem instance, in the sense that an algorithm must be general enough to be able to solve all the instances of a problem. So what's the difference between a problem and a problem instance? The problem is, for the case of the algorithm previously, a problem is the statement of the work that we need to do. So the statement specifies the type of data on which we are going to work. So this is the statement of sorting integer array, sorting integers, an array of integers. In this case, they are positive integers. So the statement of the problem can be given in this way. So given an array of positive integers, find a non-decreasing sequence of this number. Okay. So this is a general statement. It describes the problem. Okay. So this is a statement that said, okay, I want to be able to sort any array of integers. So I want to find an algorithm that, given an array of integers, or giving some number of integers, positive integers, the integers will be sorted in increasing order. So this is the problem I want to solve. And you already saw lots of these kind of problem in engineering already, maybe more complicated than this one. In computer science, the problem we want to solve, they are going to be specified quite clearly, so that we can find an algorithm to solve them, so that we can know what we want to do. So why do we talk about problems or description of problems, and we confront this with instance? Is just to say that when we write an algorithm, we write an algorithm for solving the problem, not for solving instances. So what is an instances? An instances, in the case of the problem here, is a particular array of integer. Okay. So an instances is that specific array of integer. Okay. So there are infinitely many instances of this problem, because there are infinitely many different array of integers. So each array of integers is an instances of the problems that we have described as trying to solve these integers in increasing order. So we don't want to find algorithm for solving a subset of the instances of a problem, but we want to find an algorithms that solve all the instances of the problem. So Another way to describe the sorting problem here is to list all the instances of this problem. Okay, so we say the problem actually consists of the set of all arrays of integers. So that's also the problems describing extension. So again, this may look a little bit abstract at this moment, but at the end of the semester, maybe you will understand why we design algorithms that are general enough to solve all the instances of a problem. So in this class, I'm going to define or describe a lot of problems. And for each problem, I will give an algorithm to solve it. Okay, so here the problem of sorting arrays of integers, there are different algorithms that can be used to solve them. We are going to describe these. Insertion sort, selection sort, merge sort, quick sort are all algorithms that can solve this sorting problem. Usually, there is more than one algorithm that can solve a problem. Okay, so so here we have two examples of algorithm or two algorithms that solve the same problem. One is called selection sort and the other one is called insertion sort. So there are two different algorithms. At least you can see from the description that they are not the same. The description is not the same. So you guess that these two algorithms are not the same. And I'm telling you that these two algorithms are actually solving the same problem. Okay, but they are not the same. So they are not the same from the description here. And when we will spend more time describing how these algorithms work, you will see that they are not the same also in the way they solve the problem. Okay, so from the description, we clearly say this is not the same description. So we guess that might not be the same algorithms. And when we will analyze or look more closely how this algorithm are working, you will see that they actually solve the problem in different way. And really understanding an algorithm is understanding how the algorithm is solving the problem, not just look at this written description. Okay, so now we know a little bit some terminology. We know that there is a word that is called algorithm, there is a word that is called problem, and there is a word that called instance, and these three things are different. Algorithms are solution to problem. Problems are set of instances. And we also know that there are most likely for every problem more than one algorithm to solve it. So in this class, we are going to deal with this situation where we have more than one algorithm to solve the same problems. Actually, we are going to deal with this most of the class, most of the time, but not most of the time. We are also going to introduce algorithms to solve different problems. But often we will find out that there are more than one algorithms to solve the same problems, and we have to make a decision about these algorithms that are solving the same problem. The decision is could be, well, this one looked more nice than the other one. At least there are fewer line of code. It's shorter than the other one, so we can compare them in this way. You may say, I like this one better than the other one because it is shorter. But usually shorter doesn't mean easier to understand. That's exactly the opposite. When they are shorter, they are actually, it is difficult to understand how they work. But it could be a criterion that we use to compare algorithms. Okay, so they are shorter than, there was one that is shorter in this description than the others. We can also use as criteria the language. So for example, this pseudocode use words that are in English, and this pseudocode use words that are in Vietnamese, so I would prefer the one that is in Vietnamese. So you can compare the algorithms in this way. Of course, the algorithm that is in Vietnamese and the one that is in English might be the same algorithms. It's just that the words are different. Okay, so we need to not confuse this. So there are different criteria we can use to compare algorithms. We are going to discuss some of them, but the most practical one from computer scientists' point of view is how fast they execute or how fast they solve the problem. So for us as computer scientists, we are interested in algorithms that maybe run faster, okay? Because company always want algorithms that run faster, and user also want algorithms that run faster. When you click on an app application on your laptop, you usually want this to open quickly and start to run quickly. You do not want to wait till 2 or 3 minutes for the app to execute. So, and when you communicate with your best friend on some chat application, you want your friend to read immediately what you have typed. You don't want that he'd wait 2 minutes and then reply to you and you wait another 2 minutes. So an interaction that takes 4 minutes will be totally rejected by any user. So often we are going to be pressed as computer scientists to provide algorithms that work, that are quick, okay, that execute quickly. So this is the main criteria we are going to use to compare algorithms with each other, okay, algorithms that are solving the same problem with each other. We're going to select the one that is running faster. But having said that, it's actually more simple to say that than to actually find the best way to compare the running time of algorithms, okay? So saying that this algorithm is faster than the other one, we need to be more specific by what we mean by more fast or faster. So what we're going to discuss in this lecture is only this point. How can we discover, or how can we compare two algorithms from their running time point of view? How can we say that an algorithm is faster than another? Or at least what are the specific way that people that work in algorithms use to compare one algorithm with another? So what is used in the textbook? What is used in the scientific papers to compare algorithms with each other? So this is what we are going to discuss in this lecture until this lecture is complete. Okay, so we're going to compare running time. Okay, so because running time is describing the speed with which an algorithm is solving a problem. So, but what we mean exactly by running time, okay? So running time could be the wall clock. So you code the algorithms and you clock the time it starts and you clock the time it's finished, and then you measure the time it has taken for different input sides. So here we have an algorithm that is doing this. Okay, so we have a description of a procedure that just do this. This procedure compare the clock, the running time according to the number of cycles the algorithm take to run, to execute. So we measure the time. So first we take the time before the algorithm start. the algorithm is running, then we take the time when the algorithm is complete, when it has finished. Then we take the difference between the end time and the start time. And then this is the amount of time that the algorithm is taken to execute. And then we do this for different input size. So for example, if the algorithm is sorting arrays of integers, then we want to measure the running time of this algorithm for different size of array. Okay, so we start with an array maybe that has only 5 integers, then we go to an array that has 50 integers, and we keep increasing that. And then for each input size, we measure the wall plot. So how much time the algorithm has taken. And then we can do this with different sorting algorithms. As I mentioned before, there are different sorting algorithms. There is insertion sort, selection sort, merge sort, quick sort, etc. So we can try to code all these algorithms and compare their running time. And then we select the one that has best running time for all the input that I have checked. Okay, so the one that has the lowest input running time for the input size. This is one way that a lot of people will do, okay? But this way is not perfect, okay? It might actually not measure the running time of the algorithm. It might measure other things, okay? So we are not going to do that. It is perfectly legal to do this, okay? It's going to compare the algorithm with one another. I think we hope it's going to do that. It might compare other things. Okay. So if we do this, and we run insertion sort on one laptop, and we run quick sort on another laptop, what we will measure is actually the speed of the chip on which the algorithm is working. Okay, I can do this here. One algorithm is run on an old laptop that has slow CPU, and the other algorithm is running on a fast laptop that has, for example, 2 gigahertz CPU. And you will see that the algorithm, the program that is running on the 2 gigahertz CPU has better performance than the other one. But that doesn't mean anything, because what we're actually measuring is the speed of the chip, the speed of the CPU, and not the speed of the algorithm. Okay, so if we compare algorithms according to this procedure, this technique, or this approach, we actually may not measure the speed or the running time of the algorithm, but just measure the speed of the chip on which the algorithm is running, okay, or the computer on which the algorithm is running. So in order to use this technique, we must execute the algorithm exactly on the same computers, okay? But this is not very practical. If somebody is in the United States and you are here and you do not have the same laptop, the guy in US is running his algorithms in a data center with supercomputers, and you have your laptop here, might not be possible to objectively measure the running time of the algorithms. And you can think of lots of other things that may interfere with your measurement here. One laptop is running a different version of the operating system, or one laptop is busy doing some other calculation when it's executing your algorithm. So then you will have different run times because the laptop that is running other program, other application in the same time that this is running will take more time to run your application. So you can think of a lots of parameters or factors that may interfere with a measurement like that. Okay, so a measurement like that is in principle correct, but in practice it may not yield proper measurement of the speed of the different algorithms. So we are going to abandon this approach because it is not reliable. And by the way, I forgot to mention, they may not be coded in the same way, the algorithms. So if I code something, maybe it's not very performant. If you code something, you code the algorithms, your algorithms, it might be much faster than me. So you cannot tell if you use this way which algorithm is faster. So we're going to abandon this, okay? So then which way we can compare algorithm or the running time of algorithms? So we're going to use at the beginning another way, which is going to count the number of times one particular instruction is used. So we're going to give up the wall clock measurement that we have described, I have just described previously, and we are going to try to pick an instruction, because what you saw in the code previously, there are lots of instructions, right? So we can pick one instruction in the code and count how many times it's going to be executed when the algorithm is solving a problem. So this is one way to measure the amount of time an algorithm may take. Of course, we need to pick the operation that is executed the most often in each algorithm, okay? So the approach we're going to use now is to select one instruction. I call it operation, instruction, basic because we try to select an instruction that is as simple as possible, and then count how many times it is executed to get some kind of idea about how fast algorithms are solving a problem. We're going to count how many times a specific instruction is executed in terms of the input size, okay? Because the size of the array is going to influence the size of the array that I want to sort. If I want to solve a sorting problem on an array of positive integers, obviously the number of times an instruction, if I select the right instruction, the one that's supposed to be executed the most often, obviously the number of times this instruction is executed will depend on the number of integers I have to sort, okay? In this case, changing the hardware software environment is not going to have an impact on the way the algorithm is the running time of the algorithm, okay? So the way we code the algorithms, or if we run the algorithm on different machines, the number of times the operation we have selected to count is going to be the same, no matter where we execute this algorithm. Okay, so, and we select an instruction that is in the pseudocode, not an instruction that is in the code or in the assembler. So we select an instruction that is in the algorithms, okay? So this way, we remove some of the factors that we have described previously that may bias our measurement of the running time of an algorithm. So the factor we described, like we run the algorithm on different machines, is not going to impact on our measurement. If we use a different operating system, that's not going to impact the number of times the instruction is going to be executed. And if I'm a poor programmer, It doesn't matter because we are not talking about the code. We are talking about the algorithms. So this technique to measure the running time of an algorithm at least is going to remove some of the bias we had with the clock measurement. So another things we have to do, because I said that our instruction will depend on the input, is to select the proper input. So there might be more than one input to our algorithm. So it's often when you code a function that the number of parameters of this function is larger than one. So we need to select that input that is going to be the most relevant to measure the running time, okay? So we need to select that input parameters that actually is causing the algorithms to run, or that input parameters that is causing the algorithm to take the most time, the larger amount of time. For the beginning of this class, I'm not going to consider this. We will see this later. For the beginning of this class, there will be only one parameter, so it will not be too confusing, okay? So for example, for an array of integers, so there is only one parameter, is the array that we need to sort. So now that we know that there is only one parameter, how do we measure the input size? We can consider that the input size is the number of integers in the array. So if there is only one input, there are different ways that we can calculate the input size. But here we're going to assume, for the clarity of the description, we're going to assume that the input is an array and that the input size is actually the number of integers in the array. When we will be looking at other algorithms, that could be different input size. For example, if we are dealing with graph or trees, the input size could contain nodes and contain edges, but we don't need to care about that. We may also try to solve compute the root of some polynomial, and the running time of the algorithm may depend on the degree of the polynomial. So in that case, the input size will be the degree of the polynomial. To make things easier, we are going to say that the input size is n, and describe the size of the input. And again, if we are trying to sort an array, and the input size will be described as the number of integers, and we are going to abstract this by n. Okay, so do we have everything? Okay, so there are lots of other detail here that you can read. But here's my algorithms. There are n integers in the array, so n is going to be my input size, and my loops here, my for loop is indexed with the input size, with the size of the array. Okay, so this is okay, I think I described. What did I describe? I said, okay, we're going to compare algorithms with one another, and we want to measure them, compare them along the running time. So we don't compare them in terms of the number of instructions or the language in which they are used, but rather we try to measure the running time of the algorithms. And we decide that measuring the running time by clock, taking the clock, the time the algorithms, the program execute, from the beginning when it starts to the end is not a good idea, because this may be biased by the machine on which it is running and other factors like the running time or the coding. So we decide this is not good, and we decide that we're going to measure or clock the running time or measure the running time of algorithms by selecting one instruction in the pseudocode and then counting the number of times this instruction is executed. Now, we know that the number of times this instruction is executed depends on the input. And what is the input? The input is the input size, sorry. So what is the input size? The input size is the size of the input that of the size of the instance for which we are of the problem that we are solving. The size of the instance in case of array of integers is the number of integers in the array. And we abstract this with the numbers, the number n, with a variable, sorry, the variable n, and n is going to represent the input size of the instances for which we try to calculate the running time. Now that we know all this, we have to figure out how to select this instruction that is the execute the most often when the problem is solved. So I'm calling this instruction that is executed the most often basic or elementary. Basic elementary here doesn't mean that it is because it is executed the most often, but it means it is a simple instruction, okay? So we do not want to select an instruction that is too complicated, and you will understand later in the next slide why we do this. So I'm going to select an instruction that I'm going to call basic or elementary because it is a simple instruction in terms of code or in terms of programming, okay? And we select the one that is executed the most often. Obviously, that instruction is going to be in some loop, okay? So let's look at something complicated because now what I said is too easy. So let's look at the different instruction in this code. So there are different instructions, and since the code is quite basic, every instruction can be considered as basic or elementary instruction in this code. So there is nothing complicated here. So there is this for loop that we can consider as a basic instruction. This assignment, this other assignment, this while loop, this assignment, and assignment. So these are instructions that are basic enough to be candidate to be selected to be the instruction that is executed the most often. Now, how often this instruction is executed? It's going to be executed n time. Okay, so exactly n time because I think I would say n-1, but it doesn't matter. So this loop is going to iterate from 2 to the length of array, so to n. So it is said here n, but I think should be n-1. How many times this assignment will be executed? It's going to be executed n-1 time. This is not execute, this is a comment. So it is going to be, that should not be count at all. So the cost is 0 anyway. So this is not an instruction. So the cost is 0 in terms of CPU. It's never going to be loaded by the CPU and execute. But we can say this appear n time, n-1. Forget about this one. Okay, I have this assignment instruction that is in the for loop. So that guy is going to be executed n-1 time also. The while loop, okay, one comment here. This is execute n time because it's going to be test when the length, when the loop is equal to n, okay? Sorry, when the loop is equal to n plus 1. When the loop is equal to n plus 1, so when this value, when j is equal to n plus 1, then this loop will stop. So we test with j equal to 2, 3, 4, n. We go into the loop, and n plus 1. So n plus 1 minus 2 is equal to, minus 1, sorry, is equal to 1. So the number of times this for loop will be executed is exactly equal to n. This instruction here is equal to n. But what we do in the inside the loop, we execute inside the loop for j is equal to 2, 3, 4, 5 until n. So we execute this loop for n minus 1, n minus 1, okay? So the number of times the instruction inside the loop are executed is n minus 1. All right, now how about this while loop here? This while loop here is going to be executed how many times? A certain number of times that we do not need to describe too much at this point. So the number of times is described by this expression here, by this summation. How many times this is going to be executed? This expression minus t minus 1, so we don't need to describe this too much in detail yet at this point. And finally, this instruction here is not inside the while loop, so it is executed for each iteration of the for loop. So what I have here is the number of times that each of these basic instructions are executed. Next, I have the cost. The column here, that is the cost. The cost is the number of cycle, the number of machine instructions. So that's the real cost to execute this operation, okay? The machine cost is the number of assembler instruction that is executed to perform one execution of this pseudocode. So this is pseudocode, almost like programming code. So the real cost is this, C1. The real cost of this assignment, also C2. So this is the number of CPU cycle that need to be executed to perform this assignment. The real cost of this assignment is C4, and the real cost of this while loop, each execution of this while loop is C5, etc. So what we have in this column is the number of machine instruction that correspond to this pseudocode instruction. This is the number of machine instruction. This is going to be different from each computers. Okay, so each computer has a different set of machine instructions. So the number of machine instruction here is going to be different for each computers. And we don't want to consider this. We don't want to consider how many machine instruction. We don't want to calculate how many machine instruction are executed because we want to abstract ourselves from there. Okay, so we don't want to have our calculation of the running time that depend on the machine instruction, depend on the hardware. So we abstract this by these variables. So C1 is a variable that depend on the hardware, C2 is a variable. So now if I want to calculate the running time of these algorithms, I can add the number of time that each instruction is executed. So I'm getting into something complicated now, and then we will simplify this. So this is the whole running time of the algorithms. I measure the whole running time of the algorithm by counting how many times each abstract or each pseudocode instruction is executed. Okay, so we are clear here, this is going to be executed n time because that loop has to be tested when j is greater than n. Okay, so this has to be executed, and then when j is greater than n, it's stopped. The code inside the for loop is executed n minus 1 time. Okay, It's not execute when j is greater than the condition is not satisfied for entering into the for loop. So now we know how many times each instruction is executed. And again, forget about that part here that is a little bit complicated. So we can write an abstraction about the running time of this algorithm. So if I said that the running time of the algorithms is Tn, so the running time of the algorithm in terms of the input size, I can write the expression that describes the running time of the algorithm. Okay, the expression is C1n plus C2n minus 1 plus C4n minus 1, etc. So this is actually the running time of the algorithms that count the total number of basic instruction, total number of instruction in the pseudocode that are executed. Okay, so n time this one, n minus 1, etc. And I make abstraction of the hardware. Okay, so the running time I get here is the running time that is correct, no matter where this algorithm is executed, no matter how, which way it is coded, etc. So this gives me the total running time of the algorithms. In terms of the number, the instruction is executed in this algorithm. Now I can simplify this expression, okay? So I can remove all the common factors and put it in one place. So I have one factor in n in this expression. I have two factor in n. I have three factor in n minus 1. So my factor have one factor in n should be there. Okay, all the factor in n are there. What did I do? Okay, so I just abstract this summation here. So this is my new expression. By finding we find the closed form of this summation. So these are the closed form of the summation. So make things more civilized. And now after that, I want to find the common factors. So these things here are n squared. Okay, so those factors are n squared. So I have three factors in n squared. So they are there. So this is the common factor with the constant. And I have 1, 2, 3, 4 term in n plus this guy here. So this is in n, this is in n2. So if I multiply this thing, I have n squared plus n. Here I have n squared plus n minus n and n squared minus n. So these are terms in n, and here, and here, and here, and this one. So these are the common factor. And then I have the constant. The constant is this guy here, this guy here, this guy, etc. So C2, C4, C5, and C8. Once I have all those common factors, this thing here is a sum of common factors, a sum of constant. I can abstract this sum of factor, this sum of constant by A. These things here also are constant, so I can abstract all these constant by B, and then I can abstract all these constant here by C. So this running time of the algorithms actually can be given by this expression. Okay, so A is the sum of these factors, and B is the sum of this one, and C is the sum of this guy. So this is an expression that is equivalent to the previous one. So you see that I can write exactly the number of basic operation that has been executed, the number of operations that has been executed by this algorithm. I can find an expression that describes the number of operation that is executed by these algorithms. Now let's go back to what I was saying before, that we are going to select one of these guys, one of these instructions, and measure the running time of the algorithm in terms of this instruction. And you will feel much better after that, because I think you don't want to calculate all these, you don't want to compute all these expressions, this kind of expression for each algorithms. So let's go back to what I was saying before, is that okay, so let's try to find among all these instructions, the one that is executed the most often. The one that is executed the most often is actually this one. So it is this one here. So if we look at this instruction, C5, this is equal to n squared plus n over 2, okay? This is bigger than n squared minus n, the two other factors, two other terms that are in n squared, okay? So we know that this term is bigger than any other term in n minus 1 or n. So this term is n squared plus n over 2, and this is n squared minus n over 2, and n squared minus n over 2. So this guy and this one are all bigger than this one, but this term is bigger than this one and this one as well. So we can think of instruction C5, corresponding to the constant C5, is the one that is executed the most often. Okay, so this one here, this while loop, is going to be the instruction that will be executed the most often. You will see that we don't need to do that in such a detail when we want to figure out the instruction. We will be able to intuitively guess the one that is executed the most often. So if I assume that all those guys are so simple that they can be considered as a basic instruction or elementary instruction, so all these guys in this algorithms are simple enough to be considered to be candidate to be, or they are all elementary operations, okay? So their code, the binary code or the hardware, the binary code, yes, is relatively simple. The number of machine instructions for each of these pseudocode instructions is relatively small, okay? So we can consider that each of them is simple. So now I need to figure out which one is executed the most often. I have a set of candidates of basic instruction, and my goal is to find the one that is executed the most often in order to claim or to express the running time of these algorithms only in terms of this guy. So C5 is clearly the one, the while loop is clearly the one that is running, execute the most often according to our mathematical analysis, okay? So that's the largest term among all the term in the expression, in the previous expression. So we can conclude that this guy is executed the most often. Let's say that's the case, okay? Let's say I select this guy as a representative of the running time of my algorithms. What do I get? I get that the number of machine instruction for this while loop is equal to c phi n squared plus c phi n over 2 minus c phi, okay? Why do I have this minus c phi there? Let me go back to this thing. Minus 1. Okay, I forgot a little bit where it's not important. So forget about this minus c phi. We have this number of basic instruction, this number of machine instruction that are executed. So this is the number of time this instruction is executed, n squared plus n over 2. And in terms of machine instruction, this is the number of machine instruction that are executed. So now when we select one instruction, one basic instruction among all the basic instruction in the code, we have to ask ourselves how much precision we have lost in terms of the running time. So how bad is our measurement compared to counting all the basic instruction, okay? How many times all the basic instruction are executed. So we know that if I count all the basic instructions that are executed, this is the number of, this is the complexity or the running time of the algorithm, okay? So this is the real running time of the algorithms in terms of the number of time all the basic instructions are executed. But I told you before that we are not going to do that when we measure the running time of an algorithm, but rather we are going to select one of them. So if I select one of them, it means that my measurement of the running time is not exactly the total number of the amount of time that the algorithm is taking if we measure the execution of all the instructions, okay? So if I select one of them, and I select the one that is executed the most often, actually I have a different result, right? N squared plus n over 2 is different than what I got previously. And we ask ourselves, how much precision are we losing when we do this, okay? Well, here actually we do this in terms of machine instructions. Sorry about my we are actually not, I don't want to do this in terms of machine instruction, but the example is with this. So now we're going to express how much precision we lose in terms of machine instruction. So what is C5 with respect to A, okay? C5 is one of the term in A. So when I abstract here the constant, when I represent the constant of n squared, the constant of n squared are actually C5 over 2 plus C6 over 2 plus C7 over 2. So I represent this by a constant A. Now I'm going to select only C5. And I want to know how much precision I have lost with this. Well, the precision I have lost is Y. Okay, so the relationship between C5 and A is that C5 is, or A is Y times C5. So C5 is smaller than A. How smaller it is, some constant factor, okay? So the difference between A and C5 is some constant factor, and that's what we lost in terms of precision. So the number of the precision I have lost by looking only at instruction 5 to represent the running time of the algorithm, the precision I have lost in terms of the machine instruction for C5 is y, a factor of y, a constant factor, right? A multiplicative factor. And we can reason similarly with B and with C, okay? So B and C are not represented here, but what are they with respect to 5? We can calculate this also. So we can measure what is the ratio of B in terms of C5, and we can measure what is the ratio of C in terms of C5 as well. And it's going to be a multiplicative factor. So C5 is Z times C5 is equal to B. And C5 with respect to C, it is W times C5 is equal to C. So C5 is smaller than C, and C5 is smaller than B by a constant, by a multiplicative constant. So that's what we lost in terms of machine instruction. That's the precision we lost. We lost a precision that is a multiplicative constant. And if I forget about the this level of detail in term of machine instruction, and I consider also how many basic instruction, what is the precision in terms of the number of basic instruction that is executed. If I only consider one instruction, the one that is executed, and I compare this numbers that I get by measuring the number of times this instruction is executed compared to the sum of all these other instructions, okay, all the others that I have not measured. I have not measured this guy, not measured this one, not measured this one, C4, and I have not measured C6, C7, and C8. So what is the loss I have? So of course the number of instructions and the running time that I will get if I only measure this one is going to be smaller than the sum of all these guys. But how smaller it is smaller by a constant factor, okay? 1, 2, 3, 4, 5, 6, 7 is just 1/7 smaller than the running time I will get if I measure all the basic instructions that I execute. So the running time of the measurement of the running time that is based on one instruction is going to be smaller than if I count all the other instructions that I execute, of course. But by how smaller it is? By a constant factor. And you will see in the future that we don't care about the difference in terms of constant factor when we measure the running time. So for us, a difference in running time that is just a multiplicative constant, it's not important. So we are going to, this is the total running time of the algorithms. We are going to replace this by n squared plus n over 2. This is going to be substituted by n squared plus n over 2. This is going to be our measure of the running time of the algorithms. This is smaller than this, okay, because we don't have this term, we don't have this one. And in top of it, the constant here is 1, okay? So n squared plus n over 2. This is definitely smaller than this, obviously smaller than that, because these two terms are not in my expression. The expression that measures the running time of these algorithms in terms of the expression that measures the running time of this algorithm, if I only count this instruction, this expression is smaller than this one. But how smaller? By a constant factor. And we don't care. So this is the rationale for measuring the running time of algorithms using only one instruction, the instruction that is executed the most often. I usually don't describe this in this class, but since you are the smart guys here, you are the top one. So I wanted to give you this rationale. I want you to understand this rationale for making abstraction of running time by representing the running time using only the instruction that is executed the most often. This abstraction is not the real running time. It's not how many times instruction, pseudocode instruction are executed, but it is less, by a constant factor. And in this class, difference of constant factor are not going to be considered relevant for what we want to measure when we compare algorithms. So when we compare algorithms, if there is only a multiplicative constant between the two running time, we will consider this as non-relevant. It's not relevant, okay? So having this term here, or only this one, for us, is going to be the same thing. We know it's not precise as we had calculated all the instruction. It's not as precise, it's smaller, but smaller by a constant factor, so we don't care. So this is the reasoning behind using using only one basic instruction, the one that is executed the most often. Okay, we are going to select the basic instruction that is executed the most often. So this is not very good. My English here is poor. So this is the rationale for doing that. Okay, so for now we are going to count only one instruction in the code, the one that is executed the most often. So what we have to do now when we want to express the running time of algorithm is to figure out which instruction is the most executed the most often, and then calculate how often it is executed. So now we have selection sort. You want to figure out the running time of this algorithm. So we need to get the one that is executed the most often. And then so you have many elementary operations. So the question here is what are the elementary operations? So all of them can be considered elementary operation or basic instruction. They are all quite simple. What we don't want to consider is the for loop, the whole for loop to be an elementary operation. So we don't want to do that, okay? So we only want to count. So for loop here is an operation, right? But we don't want to consider the whole for loop to be an elementary operation. We just want to consider these, the loop here, the index of the loop, or we want to consider the comparison in the if instruction, or we want to consider the assignment. These are elementary operations. So in this case here, we have one for loop, this assignment, another for loop, this comparison, and assignment. So these are the elementary operations. Now we want to find the one that is executed the most often. The question here is which one. So you can bet that this is the one that is going to be executed the most often, I think, or this for loop. Sorry, but I'm not sure myself. You can think about the one that is going to be executed. And then after that, we need to calculate how many times that guy is going to be executed. This is so let's try to describe how we calculate this. So one way to do this, I'm not sure which one I have select here, but I think I have select the for loop here to be the basic instruction. So let's see. I consider the loop loop index of the outer loop, the for loop here, and when the loop index is equal to 1, so how many times I'm going to execute this thing? I'm going from from j equal 2 to n. So for j equal 2, so there's going to be 2, 3, 4 until n, and then I'm going to run this to n. and then to n plus 1. So when this is n plus 1, this loop will stop, this for loop will stop. So this is n plus 1 minus 1, because I have run 2, so minus 1. So I'm going to execute this n minus 1 time, n plus 1 minus 2. So I'm going to run this n minus 1. You will see in the class that I'm not very good at details. I think the TA is going to be much better than me for doing that. But this is going to give you a way to figure out the number of basic operations that are executed in this loop, in this algorithm. So look like we consider this to be the basic operation, and we count how many times this loop is going, this for loop is going to be executed. This basic operation is going to be executed. The first time is going to be executed n minus 1. The second time is going to be executed n minus 2. The third time is going to be n minus 3, etc. So we can express the number of times this basic operation is going to be executed in terms of the index of the other loop. And we get this sequence of number n minus 2, n minus 3, etc. If we put this in reverse order, they give us 1 plus 2 plus 3. And this is the summation, I equal 1 to n minus 1, I, and the closed form of this summation is n times n minus 1 over 2, so it is n squared minus n over 2. This is the number of times this basic operation is executed. So your work, what you need to practice for now is figure out what is the basic operation and counting the number of times it is executed. Let me see where we are. Yeah, I will stop here. Yeah, I will stop with this one here. So we will have a break, and I think if the TA is ready, after the break, he can do some exercise with you where you calculate the number of basic operation, where you find out what is the basic operation and calculate how many times it is executed. And once the TA is done with this, we will start to look at some other issue. So I will let you practice this part, and then I will come back. Do you have questions so far? So if no question, we will take a break, and whenever the TA is ready, he will come back with you and make you do a few exercises to practice the part I have just described. You will see it's actually quite simple after a few exercises. All right, so Pham, you can have a break, you too, and then when you're ready, you can start to do some exercise. So quiet.
Hello, can you hear me?
At least I can hear you.
Yes.
Okay, thank you. So here are the exercises. I think you should work on it right now. Starting from the first one. You have about 5 minutes for the first exercise. After that, I will check. I think they are pretty simple. You can give the answer on the chat, or you can say. Oh, sorry. Okay. Have anyone got the answer for exercise 1? Starting from question A. You can type in the chat. No, not yet. Okay, that's good. The input side is N. So for question B, what is the best case scenario, do you think?
Okay, I think a student cannot answer this one because they have not seen what is best case and worst case.
Oh, actually, there is someone answered that right. Yep,
Yeah,
the
I
best
know,
case
but,
scenario is
yeah.
so when N is lesser than 3. And the worst case is otherwise. Okay, so can you identify the elementary operations and calculate the running time for the worst case instance? The answer for question C is when N is bigger than 3. Okay, so let me explain here. When N is lesser than 3, we always return 1, by the way. I mean 1 right away. Yep, either N equal to 1 or 2, so the running time should be a constant. But when N is bigger than 3, you have to go to this branch, and there is a for loop here, so on and so forth. Okay. Yep, even when N is exactly 3, we go to this branch. Oh, I forgot about the case you mentioned. When the input is 0, it should return 0, right? I made a mistake here. Yeah, so if you implement a Fibonacci algorithm, it should return 0 when N is 0 or below, and return 1 when N is 1 or 2. and the else branch otherwise. Okay, for the question D, identify the elementary operation. What is the elementary operation here, do you think, in this pseudocode? Yes, you're right, the for loop. So in the worst case scenario, when n is an arbitrary number, how many times the for loop actually run, do you think? Yep, you're right. N minus 1 times. Some of you might say that is n minus 2, but this is the explanation. In the for loop, there are always the comparison operation here and the increment of the counter. So you check if I is lesser than n, then whatever inside the for loop will be run. Yep, will run. I mean, but when I is bigger than n, n plus 1, for example, the comparison operation here still run, but the check will fail and whatever inside here will not run. So you must count even the n equal to, I mean the I equal to n plus 1 case. So that makes n minus 1 operations. Do you understand that? Do you have any question?
Okay, I think I will take it from here.
Okay.
So I need to describe the base case, the best case and worst case, and because these are questions that are a question for the whole lecture, and I have not yet covered the whole lecture. So let's look at the last part of this lecture, and then we come back to the exercise. So this is a second example of a problem for which we want to measure the running time. So this is sequential search. We will come back to see many times. So we have an input, an array. We can assume it's an array of integers. And we also have a second input that is some variable. So this algorithm has two inputs. They are not going to be both relevant for measuring the running time. Okay, so obviously, if we look at the while loop is control the upper bound of the index of the while loop is n. So the while loop, the number of times that the while loop will be executed is depending on the array L, on the size of the array L. There is nothing that controls the execution of this algorithm based on X, except maybe to stop the iteration of the while loop. So there are two inputs, but only one of them is relevant to, is considered to be an input that we will use to calculate the running time of this algorithm, and the input is the array L. And the size of this input is n, since the number of integer in this array is n. There is a Boolean initialized to false, and an integer here, I, that is going to be used as loop index value. So we start with I equal to 1, and we check whether the value that we are looking for, X, is in this entry, and then if it is, then the condition here will become true and the loop will stop. And if not, then if X, for example, is not in the array, this while loop will run until this condition becomes false, that is until I is greater than n. So we want to know what is the input size of this algorithm. So the input size is n. What is the elementary operation? So the elementary operation is this while loop here. What are the elementary operations? So there are a bunch of elementary operations, but the one that we are going to consider for measuring the running time is this one. That's the one that is executed the most often. And we want to know how many operations, we want to calculate the running time of this algorithm. We have a problem here because we cannot tell what is the running time of the algorithm. It depends on where X is, okay? So if X is in the first entry, the running time is 1. If X is not there, the running time is n. So on these algorithms, we cannot just tell beforehand what is going to be the running time of this algorithm. So we need something else that we always use when we measure the running time is what is the worst case possible scenario. So what is the worst input of this algorithm? So usually we don't measure the running time specifically for any input of size n, but we measure the running time for the worst input of size n, so the worst input structure of a given size n. So we're not going to give the running time of algorithm usually in general for all the possible input of some size, but we are going to consider the input that present the worst, that will cause the algorithm to run the largest number of iteration, or to execute the basic operation that we have selected to measure the running time the most often. It's clear here that our basic operation that we use to measure the running time, the number of times this will be executed depend on the input, not only on the size of the input, but also on the structure of the input. Okay, and that's often the case. So, so that's why here we cannot tell the running time, because just knowing the size of the input is not, doesn't make us able to tell the running time of the algorithm. So we also need to consider something else, which is the structure of the input. So there are lots of input of n integers. we want to consider the one that will maximize the number of iteration, number of execution of our basic operation. That's what we usually do when we measure the running time of algorithms. For a given input size, we also look at what is the input, what is the structure of the input that will make it that will make the algorithm to run the largest number of time. So this is called and this is an example here where we have the value x is equal to 4, and we have this array. The number of iteration is equal to 4, and if we have the same, if we have a same size array, input array, but in this order, then the value x is found immediately. So the number of iteration, number of times the while loop is executed is 1 plus 1. Actually, it should be 2, because like the TA say, we consider this until one of the criteria is false. It does not satisfy the condition of the loop. So if we look for 4, and 4 is the first entry of the array, the first time we are going to check this, all the conditions are true, all the conditions satisfy the criteria of the loop to get into it. So we will find that 4 is equal to L1. So this is going to make found true. But then we still execute this one more time to discover that one of the condition for the while loop is not satisfied anymore. So this is actually, even if x is in the first entry of the array, this while loop is going to be executed twice. So this is not correct here. It's 2, and here it should be 5. So when we don't know how many times the basic operation is going to be executed, just based on the size of the array of the input, we need to discover what is the input that will produce the largest possible execution of our basic operation. So we consider, or we say that the analysis of the runtime, of the running time, in this case, is the worst case analysis. So we talk about worst case analysis. And essentially, it means that we have found the worst instance of a given size, and then we measure the running time for this one. Beside the worst case analysis, there is also the best case analysis and the average case analysis. The average case analysis, I will not consider it today. We will study this later. And the best case analysis is a situation, that instance that will generate the smallest number of execution of the algorithm. Here, obviously, the best case is when x is in the first entry of the array. So this is going to be the best. The analysis of this algorithm in terms of best case will return running time equal to 1, and the analysis of this algorithm in terms of the worst case analysis of this algorithm will return n plus 1 in terms of the number of time the basic operation will be executed. So I already answered this question. Let me look at worst case analysis for the insertion sort. So insertion sort is a case of a sorting algorithm where the running time depends on the structure of the input side, the structure of the input. So how the array to be sorted is organized. So we have the execution of these algorithms that is pictured here the iteration of the algorithm is pictured here. So insertion sort, the way it works is that it divides the array in two, a sort part and an unsort part. And it takes the next element in the unsorted part, the part that is not sorted yet, and place it in the right position in the sorted part. So initially, the sorted part of the array only have one element. It is the first element of the array. So there is only one element in the sorted array, so this array is sorted automatically. And the unsorted part is all the other n-1 element. So again, this algorithm is very simple to understand. The first iteration of the for loop, the outer loop, consider the second element of, or the first element of the unsorted part, the second element of the array, and place it in the right place in the array. So when we consider this guy, the sorted part of the array increased by 1, and then we move this guy in his right position in the sorted part. So the next iteration, we consider the next element in the unsorted part in the array and put it in the right position in the sorted part. So 45, it goes there, so we swap 45 and 78. And if 45 is not smaller than the next one, it is his right position in the current array. Okay. So, and that's the way it goes. The next one is going to be considered is 8. So 8 will be, we will move 8 into the sorted array until it reaches the right position. And each time I move 8, I swap 8 and the next element that is larger than 8. And I do this until we arrive to a position where the next element is smaller, or we are at the end of the array. So that's what this loop is telling us, this while loop. It's running until j is greater than 0. So if j is not greater than 0, that means we have reached the end of the sorted array on the left side. And if aj is not greater than v, so if the element I'm trying to position is not greater than the next element in the sorted array, I have to find the place where this element should be. So it's quite easy to understand how this sorting algorithm works, but the running time is more difficult to analyze because how many times we are going to iterate in this loop here. So this is going to be our basic operation. And the number of times this loop will be executed depend on these parameters and this one, especially this one. So if the element is already in its right position, like here, we do not continue in the array. We don't continue in this loop, so this is just one iteration. And if the element we try to introduce in the array is the smallest one, then we have to iterate many iterations of this while loop until we get to the last position, until we get to j equal 1. So the running time of this algorithm is going to depend on how the array that we try to sort is structured, because the number of iterations or the position where we need to put the next element that come from the unsorted array, this while loop here is going to, the number of times it's going to iterate is going to vary based on the value of the next element to sort it. So for I equal to 1, so if I equal to, if I equal to 2, the number of basic operation is 1. So for I equal to 2, 78. How many iteration I do of this while loop? I just do one time, okay? J is equal to I minus 1, equal to 1, so it's satisfied. But aj is not greater than v, where v is ai. So it stopped there. We just do one iteration. If I equal to 3, we need to do 2 iterations. So first compare this guy with this guy, and then it is in the right position. Next iteration is to detect that the condition for entering into this loop are not satisfied. So we need to execute 2 basic operations when I is equal to 2. When I is equal to, I equal to 3, I think. Yeah, I equal to 3. So when I is equal to 4, 1, 2, 3, 4, it is 8. So first compare 8 with 78, 1, 8 with 45, 2, 8 with 23, 3. It's in the right position. And then 1 iteration to detect that the condition of the while loop are no longer satisfied. So we need to do 1, 2, 3. I thought it will be 4. Maybe there's a mistake here. Let me make sure. 1, 2, 3, 4. I think it's 4 here. And when I equal to 5, it does 3 iterations, etc. So what you can see, modulo the fact that the number of iterations may not be correct, what you can see is that the number of iterations executed by the while loop is not the same for each value of the for each index of the auto loop. So it is obvious that the number of iteration of this algorithm, the running time of this algorithm, if we measure this in terms of the while loop, depend not only on the input size, but it also depends on the structure of the input. So we want to figure out, in this case, what is going to be the worst possible input for this algorithm. So what's going to be the situation where the algorithm is going to run the longest number of iterations. So, and I think you can see that if the array is sorted in decreasing order, that's going to be the worst input for this, the worst input structure for these algorithms. So if it is sorted in decreasing orders, we have to swap the next element with this guy, and when we arrive to the last one, we have to motivate it back to the first entry of the sorted array. So in that case, the while loop is going to execute a number of iterations that will depend on this condition only. It's not going to depend on this one. So it's going to depend on the value of j. So first time it's going to execute 2 iterations, 3 iterations, 4 iterations, etc. So this is the worst possible input. And when the array is already sorted, like in this case, then the number of iterations is going to be equal to 1. Each iteration is going to be equal to 1. So the total number of iterations of the while loop is going to be equal to n minus 1. So the while loop will be executed n minus 1 time for all the iterations of the for loop. So this is going to be the worst case answer for this algorithm. So this is the example where the array is sorted in decreasing order. So you get this summation, and the closed form of this summation is n times n plus 1 divided by 2 minus 1. So when we analyze these kind of algorithms, we usually analyze it for the worst case. So when we report the running time of an algorithms, we usually report it for the worst case. Not for the best case. When we are going to compare the running time of algorithm, we are going to compare them in terms of the worst case. Selection sort is independent of the structure of the input. So the inner loop here, the condition of the inner loop is purely dependent on the value of the index of the outer loop. So the number of iteration because this is our basic operation, so the number of iteration of the for loop here is independent of any situation, not depend at all on the structure of the input, okay? So the number of iteration of the inner loop is going to be purely depend on the loop index. It doesn't depend on how the input array is sorted or structured. So the worst case, best case of the selection sort is the same, and it is n square minus n divided by 2. Okay, so I have finished with my material for this lecture. So what we understand is how to calculate the running time of algorithms based on the using a technique that is not biased by any factor that are independent of the algorithm. So we have selected a way to measure the running time that depend purely on the algorithms. And this way consists to select one operation and count how many times this operation will be executed in the worst case. Okay, so for a situation where we consider for a given input size the worst possible input, that is the input that will make this algorithm execute the largest number of iteration or execution of the basic operation. So what is next? Next, we are going to make more abstraction. So now we already abstract the number of machine instructions from the measurement. We also abstract the execution of all other instructions that are not our basic instruction, the one that we consider. So we already have two layers of abstraction that we have considered. That remove us from the real number of the machine instruction. Now we are going to move to another layer of abstraction. We are going to give up even the running time that we measure, actually. So we are not even considering the number of number of time the basic instruction is executed. So if we look at this algorithm here, we said that the running time is equal to n plus, in the worst case, we say that the running time is n squared plus n over 2 minus 1. So this is our running time. We still have 3 terms in this expression that describe our running time. Okay, we have n squared plus n squared over 2 plus n over 2 minus 1. So we still have 3 terms in the expression that describe the running time of the algorithm. Even though we made abstraction of the hardware, the number of machine instruction, and we made abstraction of all the operations that are not, all the basic operations that are not part or not our the basic instruction that is executed the most often. So even though we did that, we still have an expression that has several terms in it. So the next step will be to remove all the terms except the one that is the largest one, so n squared. We are going to remove all the constant, all the multiplicative constant, and all the other terms that are smaller than the largest term. So we are going to abstract even more the running time because when we want to compare algorithm with one another, we actually want to know their asymptotic behavior. So what is the running time behavior of the algorithms when the input size grows to infinity? So this is the level of abstraction that we actually use when we compare algorithm, and that's the level of abstraction we will be using for the whole semester when we are going to describe algorithms and compare them with one another. So I will let you continue to work on the exercise with the TA to make sure that you have assimilate all this part. And if you have finished the exercise and we still have time, I will start the next section of the class. If not, I will see you next week. Okay, so Pham, you can continue.
Okay, let me share my screen.
Yeah.
Yeah. We are done with exercise 1, right? Do you have any question? I think we are. Now moving on to exercise 2. So below is the pseudocode for an algorithm that checks if the sum of all the elements in an array is divisible by every single blah blah blah. You can read the algorithm here. And so what is the input size of the above algorithm? It's easy. You can type in the chat.
HUST.
Okay, that's right. So what is the best case scenario and the worst case?
The worst case.
Well, actually, there is no best case or worst case in this problem.
Oh.
Because no matter how the input might be, it doesn't actually influence the running time of the algorithm in terms of structure, right? This for loop will always run n times, so on and so forth. So D, can you identify the elementary operations and then calculate the running time? Well, yeah, the for loop, but I think we might have to count both of them, both the for loop, since they are executed approximately the same number of time every time the algorithm runs. Okay, your answer might be reasonable. It's actually another answer here. Yeah. But if you count both the for loops, both of the two for loops here, then the running time should be 2n plus 1. Yes. So there's no problem with exercise 2. Am I right? I guess that's the case. Okay, so for exercise 3, have you all written this exercise? I think I will give you another 5 minutes for this. Okay. Yes, Đào Trọng Việt given quite right answer. But again, the last for loop here, j from 1 to n is executed n plus 1 time. Because for the last time when j is equal to n plus 1, that's when the for loop actually breaks, you know. The elementary operation is actually the, yeah, Nguyễn Thị Hương Giang is right. Oh, by the way, you only have to count the number of times the basic operation is executed. You don't have to multiply by the cost here. So the C multiplied here is not necessary. It's n times n plus 1. That's it. So I believe you understand exercise 3. Do any one of you have any question? Okay. So here, the Floyd-Warshall algorithm. The input side is n. You can think of it for now as the dimension of the weight matrix. So the idea of this algorithm is that dij is the cost for going from I to j. So if going from I to k, then from k to j actually costs less than going directly from I to j, then you should update that into the cost of going from I to j. So there is 3 nested for loop here. The last one here, the j from 1 to n. So you see, it's executed the first n times from j from 1 to n. It executes whatever is inside the for loop, but it still has to check the last one time when j is equal to n plus 1. So the check condition here return false. So the for loop is stopped. You see, but for the outer loops, I from 1 to n and k from 1 to n, we can only count when the times the check condition return true. Why, you may ask? Because if the check condition here return false, then the for loop inside will not be executed. So yeah, you understand? I think you may understand by now. Do you understand by now, or do I have to explain once more time? Okay. Yeah. So can we move on to exercise 4, the last one? Or do you have any questions still?
Excuse me.
Okay.
When k from 1 to n, so it is from 1 to n minus 1, and if k equal to n, it returns false, right?
Oh, no. When k is equal to n, it still return true. and when I is equal to n, it also return true. And the for loop waiting like this. The check if j is less than n is our basic operation, right? So we are only interested in whether or not this check j less than n is executed. So it is actually executed n plus one time. For n time it returns true, and for the last time it returns false. But for the outer loops, if they return false, then you don't have to run the for j equal to 1 to n line.
Yes, I understand that. I just think that for k from 1 to n, it means that k equal to n is false. I don't think that k equal to n is true, so it's okay.
So you are thinking in terms of Python for I in range something,
Yes.
right?
Yes.
Nope. So for this pseudocode, the case k equal to n and I equal to n still return true.
Okay. Thanks.
You understand?
Yes.
Okay. Does anyone else have any question? I think not. So moving on to exercise 4. You have another 5 minutes for this, and after that we'll check together.
The input size is m plus n.
You sure? You sure about that?
Yes.
I think no. N and M are the two parts of the input size. We don't have to sum that up. So N and M, the input size. And I see Diego Vũ Tuấn Minh here. He gave us the correct answer for question B. Okay. Do you all understand exercise 4 here? Do you want me to explain that? Yes, exactly. Do you understand why we need to take into account both the for loops here? I mean, both the nested for loops. Well, that might be the case, but here's my explanation. Because N and M are unknown, so we don't know for sure yet if n squared is actually greater than 10 times m times n plus 1. Am I right? I might be wrong on this.
Yeah, you are correct.
Okay, so that's why we need to take into account both the for loops. And some of you actually gave the correct answer here.
So we have two input here, and we do not know the relationship between them. So we have to calculate. We need two basic instruction. One for the first loop on M, and another one for the second loop on M. And then we need to sum this the running time of both loops. They are two independent loops. We don't know any relationship among them because we don't know the size of N and M.
Okay, so do you all understand all the exercise by now?
Can you come back to exercise 2?
Okay. Yeah, exercise 2.
Okay, the second for loop, you return if sum is modulo of AI. So if sum modulo AI not equal to 0, you return, right? You exit the loop.
Yes. Yep.
So we don't know how many times this loop will be executed, right?
Right.
So the input size is the running time is the first for loop. So it is going to be it's going to be order of n, right?
Yes, I think so.
N. Yeah. Yeah. Okay. So the first for loop is going to dominate. So we have two for loop here. Both depend on the same input parameters. We know that the first for loop is going to run Cn time. The second one is also bound by Cn time. So we just calculate, yeah, you can, in the worst case, you can say it's 2n. Okay, so n for this one and n for this one. Eventually, we only calculate the dominant one, so we know that this one's going to be larger than this one, larger or equal. So the answer is correct. In the worst case, it is 2n. That's the answer the student got, right?
Yes.
Yeah, the answer is correct. However, we don't really care about, well, actually, I'm jumping ahead. So let's keep it there. Okay, let's keep it to 2n for the moment.
Okay.
Okay. Do you have other exercise?
Yeah, we are. I think we are done with all the exercises.
Okay. So I will continue until 11:45, and I apologize for the noise, but they are testing the fire system here. So don't be shy. Be active during the exercise or during the lecture. So if you have questions, stop me, and you should be as active as you can. Even though if it is online, it's not easier, right? It's even more difficult. So you need to be as active and as present as you can, in order to be not to be how can I say, be too distant from the material at some point. Okay, so I want to continue with the next, I will just start actually, because we don't have much time. Next thing that we can discuss about the running time of algorithms. So, and this is the last level. So we're going to discuss about asymptotic notation. So we move on to a new level of abstraction, the one that we were really going to use during this class, and the one that is really used in algorithm design. So, like I said previously, we made abstraction of the machine instruction when we calculate the running time of algorithm. And after that, we transform the expression that we had in terms of the number of machine instruction into another one that make abstraction of all of these. So now we have an plus bn plus c, which is the running time of the whole expression, okay? Of all the basic instruction. However, this is if we really want to compare algorithms with each other, this is still too much detail. We will see this, may not obvious at this point, but we will see that this is actually too many detail actually to really measure the efficiency of two different algorithms for all the possible input size, okay, for input size that can grow infinitely. So too much information. And also, second reason why we want to get rid of this is that these two terms here, especially the constant term and Bn, are going to be relatively small compared to this one when n is very large. So it's not going to play very much into the weight of the running time of an algorithm compared to another's. These two terms here are not really important. They are going to be proportionally too small compared to the dominant term. So we don't really need these two terms to compare algorithm with one another. So I'm saying this in rather quickly without motivating too much. You will understand, I guess, by the end of that set of slides. So when we measure the running time of algorithms, we are going to get rid of all the constant, and we are going to get rid of all the terms that are smaller than the big one. We only keep the largest term, n squared in this case. And then we take n squared as a measurement of the growth rate. So by how much the running time increase when we increase n, especially when n increase toward infinity. So this is going to be the measurement of the running time, the dominant term of the expression that we came up with when we calculate the number of time the basic operation has been executed. So when we calculate the number of time the basic operation has been executed, we come up with some expression. We are going to get rid of all the term except the dominant one, and we are going to get rid of all the constant also. And what we left with is called the growth rate or order of growth of the running time of the algorithms. What it represents is by how much the time increase, the running time increase when n increase. So these two algorithms, these two running time that are different, are actually the same, have actually the same rate of growth or the same order of growth. So we are going to consider that these two algorithms have the same running time, because if we get rid of the smaller term, and if we get rid of all the constant, actually the expression that we are left with are the same. It is n squared. So we will say that these two algorithms have the same running time. And we are going to compare only algorithms, or we are going to say that two algorithms don't have the same running time if they don't have the same growth rate only. So that's going to be the difference we use to measure or to compare algorithms with each other. So there are some growth rates that are very frequent, that we use very frequently. So they have name. One is called logarithm. So the logarithm is a function or an algorithm that grow by in terms of n by log n. Okay, so it goes slower than the input size. Linear is an algorithm where the running time grow at the same speed as the input size, so modulo a constant factor. Quadratic is an algorithm where the running time grow to the square of the input size. And cubic is an algorithm that grow to n cubed, so the running time is n cubed of the input. Polynomial algorithm that we say that are polynomial have a polynomial running time if they run in some polynomial of the input size. Okay, n to 2, n to 3, n to 5, n to 10. These are all algorithms that are considered to run in polynomial time. And exponential is a class of algorithms that take a running time that is exponential in some factor k, okay, 2, 3. So n here is the input size, and the running time grow exponentially in some factor that we can determine depending on the algorithm. So algorithms that are running in exponential amount of time are not good news. They take a lot of time, but there are lots of problems in practice that have this running time or this time complexity. For the polynomials, we prefer the one that have the lowest value and lowest k. And the top of one, the best running time algorithm is those that are running in log n. So we are going to try to define classify algorithm in some class, complexity class. All the algorithms that are running in log n that are bound by a function that is log n. We're going to say, let me restart this. We have three. We do not consider algorithms, we do not compare the running time of algorithm even if we look only at their dominant term. So we do not compare dominant term actually. So if I have two algorithms like here, if I had, for example, N2 and N3, I'm not going to compare N2 and N3. That's not how we measure, how we compare algorithms actually. We are going to compare their complexity class. And the complexity class is defined in terms of a function that is going to bound the growth rate of the algorithms, okay? So all algorithms that has a running time that is smaller than n squared, so algorithms that are running in log n, for example, or algorithm that running in n, for which the dominant term is log n, or for which the dominant term is n, they are going to be considered to belong to the same complexity class, the complexity class that of the algorithm that run in less or equal to n squared. So the point here is that we do not compare algorithms by their dominant term. This is not what we want to do. We compare algorithm by their complexity class. The complexity class is all the algorithms that have a running time that is, for example, smaller than n squared. So all the algorithms that have a running time that is smaller than n squared are going to be considered equal, okay, in terms of complexity. We have three categories of, and n squared is a bounding function. So if I said that, if I said that an algorithm is running in an order of n squared, big O, this is a bounding function. This expresses a bound on the running time of the algorithms. And all the algorithms that has a dominant term that is smaller than n squared are considered to belong to this class, to this complexity class. So n log n belong to this complexity class, log n belong to this complexity class. So we are not going to compare the dominant term of the running time of the algorithms. We are going to compare the complexity class to which this algorithm is belong. And there are three ways that we can define complexity class or bounding function. So bounding function n squared is a bounding function, and all the running time that are smaller than n squared belong to this complexity class. So there are three ways we can bound the running time or the growth rate of algorithms, yes. We can bound them above. So we can find a function that dominate all the others. So if we find a function that dominate log n and log n, it is that is larger than log n and log n, we say that this function is bounding above. It has a running time or a complexity that is greater than all of this guy. And we indicate this by big O. Okay, so big O means we have found a class, we have found a function that define a complexity class for which all the other algorithms that have running time that is smaller than this function, smaller or equal to this function, we say these functions are bound above. They belong to the big O class of n squared. We have two other ways to bound the running time of algorithms. One is, again, to bound above, and the other one is to bound below. So we declare a function for which the running time of the algorithms is always larger than that function. For example, if I declare that n squared is going to be my function that bound below the running time of all the other algorithms, then all the algorithms that have value that is smaller than n squared do not belong to this complexity class, okay, because their running time is lower. We want to find a lower bound function such that it describes the running time, the complexity class of algorithms that have running time that is greater or equal to n squared. We denote the lower bounding function, the function that bound below the running time of algorithms, by omega. So if I see, if you have this sign omega n squared, this defines all the algorithm that has running time that is greater than this, okay? This defines all the algorithms that have running time that is smaller or equal to n squared or big O, and this defines all the algorithms that have running time that is bigger or equal to omega n squared. In this class, they have all these algorithms, including exponential running time algorithms that belong to this. And finally, we have another bounding function that is called theta. And theta, what it does, it bounds below and above the running time of algorithm. Some algorithms can be bound above and below by n squared. Okay, for example, an algorithm that is running, that has running time or dominant term that is n squared, this algorithm can be classified as having being bound above by n squared and being bound below by n squared. So the lower bound and the upper bound of this algorithm is the same. So in this case, we say that the algorithm is running in theta n squared. We often want to find this kind of algorithms because this is a very close bound. Okay, so it's a very tight bound. We can bound an algorithm below and above by the same function. So this is good. Usually we are looking for bounds that are as close as the dominant term of an algorithm. So if I have an algorithm that is running in n log n, it is correct to say that that algorithm is in order of n squared, but that is not as tight as we can get in terms of upper bound for this algorithm. So if we have an algorithm that is running in n log n, the dominant term is n log n, it's better to say that this algorithm is bound by a function that has the form n log n, okay? So this is the bounding function. Maybe it can be more clear in this example. So this is a description of the bounding function. So the bounding function is Gn. So all the function that has a running time that is smaller than Gn, like Fn, are said to be in order of Gn. Okay, they are bound by this function. Their running time is never larger than Gn. And we try to find a GN that is as close as possible as Fn. So we always try to find a bound that is as close as possible of the function we are trying to bound. So here, it's true to say that log n is in order of n square. It is definitely boundable by n square. By Gn here is n square. Fn is log n, so it's definitely bound by this. But we can actually find a better function to bound log n. We can find log n itself. So Gn and Fn are the same. So we say that the upper bound on the running time of that function is log n. So we always try to, if we want our classification to be helpful, to be meaningful, and to be helpful in comparing algorithms, so we should try to find bounding functions that are as close as possible as the running time of the algorithms. Otherwise, if we say that everything is in N4, for example, we have no real means to differentiate which algorithm is faster. See, if if n and n square are all in N4, we don't see the difference between n and n square, and it is not very useful. So next week we will describe this notation, how they work, how they are defined, and you will do exercise on this. So they have all mathematical definition, and I will explain how to prove that an algorithm is bound above or below or exactly by some other function. And that will be it for the introduction or the description of how we measure the running time of algorithms. So we're going to use this for the rest of the semester, so that's why I need to introduce it at this point. After that, we will start with data structure. Okay, that's it for me today. Don't forget to think about how you want the final exam to be organized, and have feedback to me next week. And if you do not have any question, I will let you go to your next lecture, I guess. And hope you a nice week, and see you next week, I guess, still virtual. Question? Okay. See you next week.
Bye.
Okay, goodbye. See you next
Bye.
week.
Okay, goodbye, teacher.
Bye, everybody.
Bye.
Have a nice day.
Oh,
Goodbye.
you're there. You're still there. Good.
Have a nice day.
Yeah, you too.